Today we are going to cover Chapter 1, Section 4, Building Functions Algebraically. Combining functions algebraically. F and G are two functions with intersecting domains. For all values of x in the intersection, the algebraic combinations of f and g are defined by the following rules. The sum, f plus g of x equals f of x plus g of x. This simply means that we can add two functions together. Difference, f minus g of x equals f of x minus g of x. You can subtract one function from the other. Product, fg of x equals f of x times g of x. You can multiply two functions together. And quotient, f over g of x equals f of x divided by g of x, provided g of x does not equal 0. Now we know that we cannot divide anything by 0, so the value of the function of g of x cannot be 0. Defining new functions algebraically. Let f of x equal x squared and g of x equals the square root of x plus 1. Find the formulas for the functions f plus g, f minus g, f times g, f divided by g, and g times g. Give the domain of each. So the first thing we're going to do is add. So we're going to do f plus g of x. So we're going to take the f function, x squared, and we're going to add the square root of x plus 1. And then it asks us to find the difference. So f minus g of x. This time we have to start with f for sure because we're subtracting g from it. So we're going to take x squared minus the square root of x plus 1. Wants the product next, so fg of x. We're going to find f is x squared. And we're just going to multiply times g, which is the square root of x plus 1. F over g of x, or f divided by g of x. It's going to be x squared in the numerator and the square root of x plus 1 in the denominator. Now this is where we haven't talked anything about the domain of each yet. And for all of these, the domain is going to stay the same, and it's going to be restricted by the square root, because we know that whatever's in the radicand of a square root has to be greater than or equal to 0. So we know that x is greater than or equal to negative 1. So for the first three, our domains are going to be inclusive negative 1 to infinity. But when we come down here, we know that it can't be equal to negative 1, or we'd have a 0 in the denominator. So our domain for this one is going to change a little bit. Oops, don't want that, sorry. And we're going to have a parenthesis from negative 1 to infinity. The last thing it wants is for us to do g times g. So you just take the square root of x plus 1 times the square root of x plus 1. Which gives you x plus 1. So one last thing on this screen, our domain for this one right here is still going to be our negative 1 to infinity, because if it's not something that's defined for g, when we multiply it times itself, the domain will still be restricted to the original function. So even though we have x plus 1, which you would think would be all real numbers, it is not. So keep that in mind when you're doing your domains. All right, so we have composite functions next. Basically, we're going to plug one function into the other function. So f and g are two functions such that the domain of f intersects the range of g. The composition function f of g, denoted f little circle g, is defined by the rule f of g equals f of g of x. The domain of f of g consists of all x values in the domain of g that map g of x values in the domain of f. Now it sounds kind of confusing, but really all you're doing is taking g of x and plugging it into the f function wherever you see an x value. So let's practice that. So we have f of x equals e to the x and g of x equals the square root of x. They want us to find f of g of x and g of f of x and verify that the functions f of g and g of f are not the same. So the first thing we need to do is take our f and then write it as g of x inside. So we're going to take the function f of x, e to the something, right? And where our x was, we're going to plug in the value of g of x. So it happens to be the square root of x for this one. So when I take the g function and plug it into the f function, I end up with just e to the square root of x. Now when I start with g and I plug f in to that function, I have to start with the square root of x, and inside of it, I will place f, which is the square root of e to the x. Now, the square root of x is in this function. For g of f, the square root is on the entire function e to the x. So we can see that e to the square root of x does not equal the square root of e to the x. And if you really wanted to, you could plug in x values and make sure that that is true, but I think you can see just by looking that it's not the same. We need to find the domain of a composition. So this time we have f of x being x squared minus 1 and g of x being the square root of x. And we need to find the domains of the composition functions. So they want us to do g of f. So I have the g on the outside, and I need to put f of x inside of g first. So g is the square root of x, so I'm going to have a square root. And then f of x is x squared minus 1. So f goes inside of g, so x squared minus 1 is inside there. And it wants us to find the domain of that. So really the restriction is in the square root, because we know the domain of f of x is all reals because it's a polynomial, but I can't have a negative number in my square root, so I need to find out when x squared minus 1 is greater than or equal to 0, and that's when x squared is greater than or equal to 1. And so I need to think about that. When I square x, it's going to become positive. So I'm going to be able to use negative numbers here. So really the only thing I can't have is between negative 1 and 1. This is one of those where you could look at the graph or you could test numbers. Remember we talked about this not too long ago. If I plug in a negative 2, I'll get 4, which is positive or greater than 1. If I plug in a 2, I get 4, which is greater than 1. If I plug in 0, then I get something that's false. So I can't use the numbers in between here. So my domain is going to be from negative infinity to 1. Negative 1, sorry. And from 1 to infinity. So the next function we need to do is f of g. So this time we're going to take the g of x function and plug it into our f of x function. So we're finding f of the square root of x. So in our f function, we have x squared minus 1. So where our x was, we are now going to put the square root of x. So that's going to give us x minus 1. But we have to go back to the very beginning for each of these functions and figure out this, the domain of this one was all reals, but our domain for the square root of x is only positive numbers. So we're looking for things that are greater than or equal to 0. So that still is going to be our domain for our composite function, because if it didn't work for g to begin with, it's not going to work for f of g. So we are going to have from 0 to infinity. Even though it looks like it should be all real numbers, it's not, because the restriction of our original function was that x has to be positive. Decomposing functions. For each function h, find f and g such that h of x equals f of g of x. So our first one here is h of x equals x plus 1 quantity squared minus 3 times x plus 1 plus 4. So if you notice, you have something that looks like you've put inside a set of parentheses or where an x might be. So if you just look at this function, what are we putting inside? Well, we're putting x plus 1 where we would normally see an x. So if we look up here where h of x equals f of g, the g of x should be equal to what looks like there should be an x. So we're going to say g of x is going to be the inside function because it's inside of f. So it's going to be x plus 1. And our f of x function is going to be what we think this polynomial is without our x plus 1, just with x in. So x squared minus 3x plus 4. So I can check that by taking my f function and plugging my g in. And if I do that, I end up back where I started. So I know that I have done it correctly. So my g of x is x plus 1. My f of x is x squared minus 3x plus 4. For this function over here, I have the square root of x cubed plus 1. Well, what does it look like is on the inside? X cubed plus 1. So we're going to let g of x equal x cubed plus 1. And if I were to replace x cubed plus 1 with just an x, my f of x would then be the square root of x. So if I took and rewrote f of g of x, I would end up back where I started, square root of x cubed plus 1, so the answer would be here. G of x equals x cubed plus 1, and f of x equals the square root of x. For modeling with function composition, this example has to do with medical procedure known as angioplasty. Doctors insert a catheter into the heart vein through a large, I don't know how to say that, peripheral vein, and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. Find the volume after t seconds. Well, the first thing we need to do is figure out the formula for volume, right? So if it is increasing at a constant rate of 44 cubic millimeters, then our volume is going to be 44 times however many seconds it's inflating, right? So at 0, it's 0. At 1 second, it's 44, so on. So then they ask, when the volume is v, what is the radius? Well, if this is a balloon, it's spherical. So what is the formula for the volume of a sphere? You may not remember this. 4/3 pi r cubed. And if I solve this formula for r, now you may not believe me right away, but you can do that easily. Let's come down here so you can see it. We would multiply by the reciprocal, right? And we need to divide by pi. And take the cube root. So we've got the cube root of 3 over 4 pi v. Kind of ugly, but that's what it is. So it wants us to write an equation that gives the radius r as a function of time. What is the radius after 5 seconds? So now where I see my v, I'm going to put in what I originally had. So it's just a substitution. I'm going to have the cube root of 3 over 4 pi times